Hey everybody, welcome back. This week, week 12, we dig back into structural equation modeling and path analysis. Last week we talked about some basic path models and how to approximate many of the statistics that we use already in a path analytic or SEM framework, which was super cool. And this week we dive into some more advanced topics. In particular, we're going to focus this week on mediation analysis, which is a really cool approach that is relatively easy to implement using SEM, which is awesome. So just a little bit of a review, going all the way back to, was it week 2 or maybe week 3? What kinds of questions does mediation answer? We talked about the difference when we talked about moderation and studying interaction effects. We also talked about how moderation differs from mediation, which seems to be the million-dollar question all the time. So mediation is about a process. So a question about mediation concerns the process by which a predictor variable affects an outcome, last part's really important here, through a third variable. So it's the process by which a predictor variable affects an outcome through a third variable. Another way to think about this in more conceptual terms, does X, our predictor, predict M, our mediator, which in turn predicts Y, our outcome? So there's 3 sort of variables, but there's actually 2 different levels of prediction. X is predicting M, and M is predicting Y. A sort of practical example here, does a more positive classroom climate improve students' attitudes about writing? And those attitudes about writing, in turn, predict higher grades. So we've got classroom climate is on the left, impacting students' attitudes in the middle, impacting writing grades on the right. And this is related to some work we've done around students' motivation in writing. So as you can see, compared to questions, research questions, which involve a handful of variables, 1 or 2 variables impacting each other, mediation is very useful for understanding a more complex process, even compared to moderation or regular regression. And so it can be really useful in the social sciences in a lot of ways. So here's a little bit of a refresher. Here is our standard regression equation. Y, the outcome Y for a given person I is equal to some intercept, which we'll call here, let me get my little pointer here, some intercept, which we'll call beta 0, plus some slope times a predictor, which we'll call X, plus error. And mediation is actually an extension of linear regression. Remember what I said at the beginning of the semester, everything is regression, right? This idea of a linear model is very pervasive. So mediation is really an extension of this, and typically we display it as a path diagram. So a regular regression looks like this in path diagram format. Classroom climate predicting our outcome, achievement. Classroom climate is the independent variable, achievement is the outcome, and the arrow here, this path coefficient, is equal to the slope, or the beta coefficient, or beta 1, right here, which is equal to 0.3. For now, we're going to call this the C path, also called the total effect. And this is, I'm going to extend this simple regression example and show you what happens when we add a mediator. So for now, let's keep track of this and just know this is the C path, also called the total effect. Okay, so when we layer on mediation, mediation builds on that basic linear regression model with classroom climate predicting achievement by adding a third variable. In this case, it's students' writing attitudes. In mediation, the third variable comes in between X and Y, ideally in terms of time, but at least conceptually. So X leads to the mediator, which in turn leads to Y. So it looks something like this. So classroom climate predicts a change in attitudes, which predicts a change in achievement. And there we have a nice mediation model. Okay, so let's come back to this, C path that we found before. So before, when all we had was the relationship between climate and achievement, we called this the C path, and we called it the total effect. in mediation, since we now have the addition of a mediated pathway through attitudes, this is called C prime path. That little apostrophe there, usually in mathematics, is just pronounced prime. So C prime path. And now it's called the direct effect because it represents the direct relationship between climate and achievement. So the idea is when you introduce a mediator, like attitudes, the C path, or in this case the C prime path, should get smaller when you add in a mediator. So the relationship is the C path like this when there's no mediator, and when you add it in, that relationship should ideally get a little bit smaller. And so it's called the C prime path. And the idea is to test, one of the things we can test when we study mediation is whether or not that C prime path is still statistically significant after we account for a mediator. Okay, so to do this, you first need to estimate a couple other things. What we're calling, no surprise, the A path and the B path. So the A path is the relationship between climate and attitudes. This is a simple regression. How does classroom climate predict change in attitudes? And we'll call that the A path. The B path is the relationship between attitudes and achievement while controlling for climate. Because notice there's also another arrow going into achievement. Over here, there's just one arrow going into attitudes, so that's a simple linear regression. This is actually kind of a multiple regression, where attitudes is predicting achievement while controlling for climate. According to some fun and fancy math, the product of the A path times the B path is equal to the C path, the original effect without the mediator, minus the C prime path, which is the path down here after we've included the mediator, sorry. So another way to think about this, the indirect effect, which is the opposite of the direct effect, is equal to the total effect minus the direct effect. So the total effect is basically the sum of the direct and the indirect effect. So direct effect is here, indirect is here. And the relationship between all those paths tends to hold as long as your two predictors here and here are continuous, which is pretty cool. And so if A times B, what we're calling the indirect effect, which is literally the product of those two slopes, is statistically significant, then mediation has occurred. If it's not, then mediation has not occurred. There's essentially all the action is down here in the direct path and very little in the indirect path. Okay, so we're going to do a little practice here, and you'll find a practice sheet and then a key in Blackboard. So you'll see practice with mediation models and then mediation models key. It looks like this. So we have this situation here where we are trying to fit a mediated model where we're trying to understand overall physical health. So that's a self-report of how healthy you feel. And we want to understand the relationship between being conscientious, those behaviors like washing your hands a lot, although, wow, that's different in this context, right? As where we are now, where we're living now. But anyway, there are these sort of conscientious behaviors that people can do to look out after their health. A conscientious mindset, I should say, that impacts the types of behaviors that you do to take care of your health, which might in turn impact your overall physical health. And so given that model, I'd like you to identify all the paths, A, B, and C prime, identify the indirect effect, the direct effect, and then the total effect. And finally, which paths need to be significant in order to say that mediation has occurred. So like I mentioned before, you'll find a handout on Blackboard that has this exact practice and these questions, and then you'll find a key that walks through the different paths and how it all works. So if you have any questions, we can absolutely talk about it during next week's content review and article discussion. Okay, so now that first segment was just an overview of sort of the logic of how a mediation model works, a little bit of the mathematics that goes into it, and also how it all fits together, kind of the relationship between the direct effect, the indirect effect, and the total effect. I kind of yada-yada'd through a really important portion of this, which is how you actually find the significance of the indirect effect. Basically, what I said earlier was, if you find that the indirect effect is statistically significant, then you've found that mediation has occurred. Yay! Actually, it's not quite that simple. Finding the significance of this, this product here of two slopes can be a little bit tricky. There are, in fact, lots of different ways that you can test this significance. There's what's called the test of joint significance, also called the Baron-Kenny test. There's the Sobel test, and then there is the use of what are called bootstrapped confidence intervals. These are increasing in their sort of complexity, but they also kind of are going from most to least rigorous. And so the current belief of all these methods, bootstrapping is currently the most preferred. Although you can test all of these in Stata, I'm going to show you how to test all of them, but I will focus on how to obtain bootstrapped confidence intervals, which is the, at least currently, in this state of age, the kind of the state of the art for finding the significance. But the cool thing is, this interesting paper by Hayes and Charcow actually found that these methods agree with each other about 90% of the time, which is cool. So while it's really a good idea to use the most rigorous method, these other methods, the Sobel test and the Baron-Kenny test, the joint significance, tend to work pretty well too. Okay, so we'll start with the test of joint significance. Again, just big picture here. What are we doing? We are trying to articulate the different ways by which you can figure out whether or not the indirect effect, right, this path going from climate to achievement, is significant. And so we're going to walk through 3 different methods for how to do that. The joint significance test is easy. It basically says if the A path is statistically significant and the B path is statistically significant, the A times B path is also significant. As you might imagine, this is a very liberal test, which means it has a very high type 1 error rate and is usually used as a supplement to other methods. So if we're looking at our results here, if the A path is 0.25 and statistically significant, and the B path is 0.28 and statistically significant, following the joint significance test, we would have mediation because both of these paths are in fact statistically significant. Okay, so then there's another approach to this which is called the Sobel test. And this was developed by Sobel in 1982. The only problem with the Sobel test is, so remember the Baron-Kenny test was a little too liberal. You tended to perhaps over-promise on finding mediation when it might not have existed. The Sobel test is actually conservative, which means it has a high type 2 error rate. So that means that sometimes you might miss a mediated relationship when it actually was there. How the Sobel test works, essentially, it creates a z-statistic by taking the product of A times B, which is the slope of A times the slope of B, and dividing by this real mess here, the square root of the square of B times the standard deviation of A plus the square of A times the standard deviation of B. Actually, that's the variance, I think. I think that's squared. So what all this is it's trying to come up with a standard error. It's trying to adjust and find a way to standardize the product of 2 slopes, which is a little tricky because slopes are notoriously difficult sometimes to be considered normally distributed in their sampling distribution. And so that's basically how the Sobel test works. You end up with the z-value. There's a really cool online calculator for this where if you know the beta values and the standard errors, which you get from any standard statistical package. You can plug those in on, this is Chris Preacher's website, and it'll give you an estimate of the Sobel test. It's also used for the default estimates in Stata. So basically we can run a little command after we run our structural equation model in Stata, and it will actually use the Sobel test to calculate whether or not those indirect effects are actually significant. Okay, so that was approach number 2. Now we're going to talk about approach number 3, which of course you know I love because it's cool. It's called bootstrapping, and this is something that we've talked about before. And it's a really good fit to fix this situation. So just to remind you, before we talked about bootstrapping when we thought that there might be a problem with some of the assumptions of our regression model, particularly things like normality of residuals and heteroscedasticity. Those are problems which can often be relatively easily corrected for if you just bootstrap your model, which produces more precise and accurate standard errors and allows you to make stronger inferences about the significance of your coefficients, of your variables, which is really good. The Sobel test is another example of a time when bootstrapping might be able to improve, because the Sobel test assumes that the distribution of slopes in a population, the sampling distribution, is actually normal. So in the universe of slopes that could exist out there, of indirect slopes, we are drawing from a normally distributed population of slopes. And it turns out, after a lot of methodological research, that's rarely true, except in really, really large samples. So if you have a really big sample, you can feel a little more confident that you are on good ground with the Sobel test. But thankfully, bootstrapping is a really cool resampling technique that essentially can be taken to non-normal data. We learned about it earlier this semester. And you can use it to bootstrap something that you think is non-normal to then approximate it in a normal population. And so that's basically what we're doing when we're applying bootstrapping to the significance of this indirect effect, which is A times B. Okay, so I don't know if you've seen this slide before or not. This is from Tim Hesterberg, who wrote a really cool article about bootstrapping that's in the Assumptions Week, I think, week 4. Oh, they're all flying by. But this is from the Hesterberg article. Again, the big idea is when we sample, we are assuming that we're sampling from a population that has an unknown mean, mu. We take one simple random sample, and that sample itself may not be a great approximation for the underlying population. But if we take that simple random sample and we resample it hundreds or thousands of times and then take the distribution of that statistic, we end up with something that ends up being much more normally distributed. And so it's very computer intensive, which is less important now because we have really fast computers, but it's an extremely useful approach, particularly in cases like this. Oop, I don't want to show you my email. Okay, so, and this is just another visual for the bootstrapping process. This comes from Seb Rashka. This is just an example. So here's your original data set. You have 10 observations. And when you draw a bootstrapped sample from that, you sample with replacement. So that means people can be drawn more than once in the same sample. So here we have person number 8 in sample 1 is included 3 times. In sample number 2, person number 1 is included 3 times, and so on and so forth. So the idea is any one of these samples is going to have the same problems that we'd be facing with the original data set. But if you do this 100 or 1,000 times, you sort of smooth out some of that non-normality and end up with something that is nicely distributed. Okay, so the same logic applies when we're bootstrapping our indirect effects. What happens is, under the hood, the software is going to create thousands of simulated data sets using resampling from your original sample with replacement. Basically, you're going to pretend as though your sample is the population, and you simulate from that. And then with each sample, it's going to rerun the analysis once in each of these thousands of samples and generate a distribution of estimates, and then use those estimates to create a 95% confidence interval. So basically, if you have 1,000 estimates, the 95% confidence interval is going to start at number 250 and go from number 250 to number 9,750, which is pretty cool. And the idea is, if 0 can't be found in that interval, then at about a p-value of 0.05, that effect is significantly different from 0. So you look at a confidence interval then of bootstrapped estimates to determine if the indirect effect is significant. So that's the third, the fanciest, and I think the most fun approach. My demonstration video sort of walks you through how to interpret all three of them. So you'll learn a little bit about how to do all three: Baron-Kenny, Sobel, and bootstrapping. All right, so we're going to talk briefly a little bit about effect sizes for mediation. I try to cover a measure of effect size for almost all of the methods that we talk about in this class, because practical significance is important. That's probably kind of an obvious statement, but it's always important to think about, okay, here's what the p-value is, here's the estimate, but what does it mean? How large is this effect? Is it meaningful? Is it important? So on and so forth. So there are lots of different ways to calculate effect sizes for mediation analysis. There's a great article by Chris Preacher and Sean Kelly back in 2011 that walks through a bunch of these. So I'm just going to highlight a couple of them that I think are cool and relatively easy to grasp as kind of a first cut. So percent mediation is a nice one, as is the completely standardized indirect effect. So percent mediation is usually represented by this character here, capital P, lower, what do you call it? Not lowercase, subscript m. And the completely standardized indirect effect is usually represented by AB, lowercase, and then subscript CS for completely standardized. So AB is the indirect effect. It's the product of the A and B paths, and then CS is completely standardized. So I'll walk you through a little bit how these work. So percent mediation basically works like this. You take the product of the A and B path, your indirect effect, and you divide it by the indirect effect plus the direct effect. So it's kind of like a fraction or percent of the total effect that actually is mediated. And that, given the math, we know is equivalent to AB divided by C, which is the total effect. So that would be the relationship between climate and achievement without including attitudes. So, so it's interpreted as the percent of the total effect that is the indirect effect. The cool thing about percent mediation is you can use it with either unstandardized or standardized estimates. It doesn't matter whether your estimates are standardized or unstandardized. So just an example here, how to calculate this. The indirect effect here would be 0.25 times 0.28, and that, according to my PowerPoint slide, I'm going to trust it, is 0.07. The direct effect down here is 0.05, so that means the total effect is 0.07 plus 0.05, so that's 0.12, which means that the percent mediation is 0.07 divided by 0.12, so a little over half. So about 58% of the total effect between climate and achievement is actually mediated through attitudes. So that's quite a bit. More than half actually is flowing through attitudes. So a few notes about percent mediation. The direct effect, that C prime path, sometimes can be larger than the total effect, and that's called inconsistent mediation. So that's when signs start to switch a little bit. When you start to account for other variables, you get positive and negative values. So in this case, if you end up with a direct effect that's larger than the total effect, so in other words, if you calculate percent mediation and it's above 1, then take the absolute value of C prime before calculating that effect size. So if you end up with a proportion greater than 1, that's what you want to do. All right, so then we have the completely standardized indirect effect. This one also is pretty cool. So again, here's our notation. AB, completely standardized, is equal to AB times the standard deviation of the X effect divided by the standard deviation of Y. And basically, this is the same thing as the beta standardized version of X times the beta standardized version of Y. So we talked about beta coefficients back when we studied advanced regression. So basically, you have two steps here. One is you need to ask the software for standardized estimates, which is the same as we did for confirmatory factor analysis. So comma stand or standardized. And then you multiply them together to get the effect size. So it's now a standardized version that will be similar. It's basically interpreted in terms of standard deviation units, which is nice. So if, for example, these were standardized estimates, 0.25 and 0.28, let's suppose they are, we would just multiply them together and we would end up with a completely standardized indirect effect of 0.07. In terms of what that means, the other effect size that we talk about a lot is Cohen's d, which is also a standardized effect size. It is typically ends up being much larger than indirect effects. Indirect effects tend to be fairly small in most things that we study in social sciences. So those standards for interpreting small, medium, large are a little much. So for example, 0.1, 0.3, 0.5, which is what we think about for Cohen's, it's probably not that extreme. 0.07 would be a small effect, but 0.3, for example, that's a pretty large indirect effect in terms of the overall relationship. Okay, so the last thing I have here for you is a sample model with some output to help kind of put all this together. And so this is that model that you did practice on earlier. So how conscientious someone is impacting their behaviors, which impacts their health. I actually ran that model and kind of walked through the different things that you're looking for in Stata. So the three elements we're looking for are conscientious, health-related behaviors, and health, and overall physical health. So this is an example of some Stata output that you'll get when you run this. So here's the relationship of conscientiousness on behavior. So look back to our diagram. Conscientiousness on behavior. So that's the A path. That has a value of 0.5. So here we have the models that are predicting health. So here's the relationship between behavior and health. So that is this model right here. So that's the B path. That's equal to 0.4 or 0.39. And then we have the relationship between conscientiousness and health, and that's about 0.26. That's the C prime path. So A path, B path, C prime path. And the colors should match from your handout as well. So the coefficient, that's the slope. The standard error is the standard error. The Z is the test statistic. This is the p-value, p greater than absolute value of Z. And according to Baron-Kenny, we would just look at the A path and the B path and ask, are they statistically significant? And they are. So according to the test of joint significance, we do have mediation. If you want to interpret the Sobel test, you have to ask for the indirect effects, and I show you how to do that in the Stata demonstration. And here you'll see the indirect effects here are separated by the table. So here is the indirect effect from conscientiousness through behavior to health. That's the only indirect effect we have. And here the coefficient is 0.21. Here's the standard error, the test statistic, and the p-value. So you would report the 95% confidence interval for this. And if that confidence interval does not contain 0, then you have mediation. Same thing, you can look at the p-value. Okay? And down here under direct effects, this is the direct effect. So this is the indirect effect. This is the direct effect down here. The relationship between conscientiousness on health, and it's 0.26. And again, you would interpret the confidence interval there. Okay, so then we have the bootstrapped test. So the only difference here is we've asked for bootstrapped estimates, and we're just looking here at, again, the confidence interval to see if the confidence interval contains 0. That's all we're looking for. All right, so that covers the main effect, the indirect effect, the direct effect, and then this is the total effect. The total effect is the total relationship between conscientiousness and health-related behavior. So just a few other notes. I talk about this again in the Stata video, but keeping straight on those terms is really important. Here's an example of how you report mediation analysis. So here's the A path, the B path, and the C prime path. In parentheses is the C path, or the total effect. All these things are statistically significant. And you would say there's a significant indirect effect of conscientiousness on overall physical health through health-related behaviors. AB, that's the indirect effect, is equal to 0.21. Bootstrapped confidence interval is equal to this. And the mediator accounts for about 44% of the total effect, and that is the percent of mediation, so it's 0.21 divided by 0.47. Okay, phew. So that's just a little walkthrough of how this all works. You should have the tools you need to start to tackle mediation, which is pretty cool. And I think I show you an example of mediation in SEM as well, using latent variables in the video. So that's your next step. Next week, now for something completely different, we will be tackling multi-level modeling. Just a little exposure to multi-level modeling. It's the first of 2 weeks where we'll talk about that. Alan Aycock, I believe it's chapter 15, has a nice treatment of multi-level modeling. There'll be a content review and an article discussion. And of course, the weekly reflection is due by Monday. So I think that's all I've got. The definitive book on mediation is by Andy Hayes. I mentioned him a little bit earlier. It's called Introduction to Mediation, Moderation, and Conditional Process Analysis, a regression-based approach. It's super cool. It also walks through more complicated types of mediation, like moderated mediation and mediated moderation and all sorts of cool stuff. It really goes to the next level, but it's a great book with lots of really good examples as well. And I think that's all I've got. So hopefully you enjoyed this, and good luck tackling the assignment in Stata.